Wow. Hello, everybody. So many people. So it's great to be here. It's a bit of a mission to get here. What with COVID and Brexit, there's lots of forms, but I managed to get here, so I'm here. And yeah, it's great to be here. And thank you. So first off, sincere thanks to the guys. It's putting on a great event here, and it's just good to see communities come together again. We've all had some difficult times, so yeah. So I'm here to talk to you about Project Sigstore, and ironically, this is a lockdown project. It was started during lockdown, okay. And but I'll do a little bit of an introduction to myself. So I work at Red Hat, and a security engineering lead in our office of the CTO. We have a group that focuses on emerging technologies. And so I've got a team of about 8 engineers, some really great folks. And we work on all sorts of things, confidential computing, trusted compute, as we saw before, TPMs. But we started to pivot towards secure supply chain because it's becoming such of a problem space as recent. You would have seen there's been a lot of stuff in the press. I'm predominantly a software engineer, so I'm all about defending, but I volunteer for the Kubernetes security response team. So there we have like a HackerOne bug bounty program. So I typically stay involved with vulnerabilities and trying to get developers to own that it's their code that caused the problem, and then triaging a patch, having a responsible disclosure system, all this sort of stuff. Yeah, and I do various other things. I've been involved with the Open Source Security Foundation. There's some interesting work that's going on there as well. Great, so today we're going to do an introduction to what is a supply chain, okay, and what are these common security attacks. Okay, we'll give some examples of those attacks. They're going to be very high level. I'm not really going to go too level on these, okay, so that we can get a few different examples in. We're going to do an introduction to sigstore, and then I was going to do a demonstration, but might shy away from that with the time that we have, and whenever I do demos, they break. So, let's see. Maybe I'll feel brave. So what is a software supply chain? Okay, so predominantly what we're talking about here is it's a mixture of people and machines, okay? 2 very problematic areas. So typically you'll have your developer who writes code, or they write a change for an existing code base, okay? And they will be the start of the chain. Predominantly, they are the start of the chain. So they will commit their code, okay, and then you might have another human who's a reviewer. They'll look at the code and they'll say, looks good to me, okay. Then you'll start to get the machines that will be involved. So you'll have your build system. So you might have integration tests, unit tests, security lint scanners like CodeQL, Bandit, various different projects will look at the code, check that it is of the right formatting and so forth. And then typically what happens is the build system will generate some sort of artifact, okay? So that could be a package, like a Python package, or it could be a container image, or it could be consumed as yet another code dependency by another project. So another project could use your software as a library or a module or a dependency in their code base, effectively. And this is what we have with this with this supply chain. And then eventually we get the consumers, okay? And this is the people that use software. So this is your users. And I think this is where it gets really interesting with open source. The people that use open source software are really, we're talking health, banking, military, finance, critical infrastructure that we really rely upon, okay? So I think we often take that for granted. When you wake up in the morning, the systems that you rely on to go about your day, they're at risk from various types of attacks, okay, which we started to see increasing, which I will get onto now. So I'm going to, there's a lot of kind of splats here to show areas. We're going to walk into these in a bit more detail, but there are multiple junctures where people can compromise a secure supply chain. So people can be compromised, their identities can be stolen, there are build systems that are quite often exploited, especially with open source projects, because a lot of the time the way they're configured is open. Anybody can go and read the YAML, the JSON files, etc., that dictate how that build system should operate. So they're open to read and scrutinize. And then there's all these other sort of attacks, which I'll walk into as we go through this. So one of the common ones, oh yeah, and going a bit too quick there. This actually came out a week ago. Sonotype have seen, they reported there's been a 650% increase in supply chain attacks. And a majority of these are exploiting open source systems. Okay, so I think that's the kind of a good reflection of how serious things are. So we'll start off with some common supply chain attacks. The first one is what we call a rollback, a replay attack, or a targeted attack. Okay, this essentially is a case of, predominantly it happens with update systems, okay, or package managers. So somebody will say, I want the latest version of widgets, okay, and then the system will reply to tell them what that version is. They will then pull that version down, they'll install it, they'll restart the service, job done, okay. Now what happens is quite a lot of nefarious mirror or a proxy can be involved so that a targeted attack happens. So it's not particularly for everybody. It might be a small group of people are targeted for an attack. And they believe they're getting the latest version. But the latest version is probably a very old version which contains a nasty CVE. Okay. And you can see here the example of, they're led to believe that 1.9.2 is the latest version, whereas it's actually 1.9.4 and 1.9.2 contains CVE XYZ. And this has happened a lot. We've seen this in Fedora and different packaging systems. There's lots of finer points to this. I've kind of put this as a high level, but this is predominantly what a targeted attack is about. The next one is good old key compromise. Okay, it happens all the time. And one of the many problems with key compromise are the trust models. So there's something called tofu. Anybody heard of tofu? It's not the vegan food. It's trust on first use. Okay, so predominantly what you'll do is you'll go to, it's like when you create an SSH connection for the first time. It says, do you trust this machine? You put yes. Trust on first use. Every time you repeat a visit to that machine, you've established that trust. Okay, and a similar thing happens with keys. Okay, predominantly PGP, GPG. What happens is you retrieve a key from somebody, you believe that person to be that person that they claim to be, you import that key, you trust it, and from there on you've established your trust on first use. And the problem with this model is when a compromise can happen. Okay, now there's one thing, if you know that the compromise has happened, there are steps that you can take to revoke the key, but it's when it's not known about, that's the real problem. So when a key compromise occurs, and then you're assuming that this is Linus signed this. Do you see what I mean? It's signed with his PGP key. Everything is great. It's wonderful. I can trust this. It's exploit free. It's not been tampered with. Okay, and a lot of the time, what we're seeing is these keys are stored on the same website as the actual artifacts that you're retrieving, and a lot of the time they're platforms that get hacked all the time. So you go to this platform and you say, I want to verify that a particular artifact is signed by the person that claims to be the maintainer of that project or the owner of the software. And you're actually retrieving the software and the keys from the same source. So we actually go into that a little bit more shortly. But the main thing I wanted to illustrate here is very hard to detect when a key compromise happens. And this is kind of leading into the area where sigstore comes into play. Okay, another attack that you've probably all heard of. I imagine some of you probably know it much better than me and you've studied this in detail, but there's a SolarWinds attack. Okay, and effectively a dynamic link library was compromised, backdoored, okay? And that was accepted because it was signed by a certificate that had been compromised effectively. So it appeared to be a trusted trusted piece of software. But evidently it wasn't, because what happened was this would then spawn a command and control server, which would then leak private data out to criminals and hostile states, that sort of thing. And the result of this was that many US government sites, military systems were attacked and compromised. And we still don't know to what degree, okay? Another one, this is around swapped hashes and artifacts. This one happens so much. Linux Mint, the Linux distribution, some of you might have heard of. They had a WordPress site, and on there they had an MD5 checksum of the ISO image. Okay, so you download the ISO image, you run MD5 sum, it spits out a digest. You look at the one on the website and you think, great, I can trust it. Okay, but the problem is somebody swapped out the ISO, and while they were there, they swapped out the digest as well. Okay, so again, another example of this problem of people storing cryptographic properties on systems that are exploited, okay, and are trivial for the people that want to exploit these systems. They're trivial systems to attack in the first place. Another example of this, and I don't want to pick on any projects, but it's key to look at this to get an understanding. Anybody heard of Tails? Yeah, okay, seen a few nods there. So Tails is a Linux distribution that is, so I guess core to its philosophy is privacy. So it's utilized by whistleblowers, journalists, people that need to leak information, okay, and are probably targets because of those actions that they're taking. So again, you download the ISO image and you get the cryptographic keys to verify it from the same website. So again, somebody, all they have to do is swap out the ISO and the keys. Now, you might have visited before and already had the key and noticed that it's changed. In that case, you're covered. But when we consider this trust on first use model, where it's people for the first time are visiting a website, they don't know about that. They have no past association, and there's no authority to vouch for the identity of that particular individual. And as you can imagine, if a whistleblower's system is compromised, human lives are at cost. It really is that serious. So another one, kind of coming back to open source. Did anybody hear of a CodeCov attack at all? So CodeCov is short for code coverage. Okay, so the idea is that your code is passed out and they calculate how much coverage of unit testing you have. So do you have a good unit test coverage for your software? A high score suggests that your software is highly tested. So it should be robust and relatively bug-free. Now, CodeCov had a bash uploader script that people would use. So what they would do is they would have a curl bash statement, and this would sort of send off a sequence of events that would get your data up, and then you could render your graph around your code coverage. And we've seen so many of these curl bash exploits that are happening that it's just, we'll go into this a bit more, but it's just a common thing that we see all the time. So somebody managed to compromise the script. Okay, they swapped the script out with something that would leak all of the secrets from people's build systems, so GitHub Actions and so forth. So if anybody had like developer keys, GitHub keys, secrets, any sort of sensitive materials, it was leaked by this script effectively. And this was pretty serious. It happened in Kubernetes. We had to go fishing to find them. HashiCorp, Twilio, Rapid7. It's a big e-commerce company that were affected. And they're still out there as well. There's still instances out there. I mean, they fixed the script still, but there are people that are not even aware that this happened in the first place. Okay, another one. Again, this is really simple, but I love the simple ones because they work. Do you see what I mean? You often think it's the really complex stuff, but the simple stuff is just, you think, how did they think of that? It's so simple. And for this one, some of you that develop on GitHub, you'll know you make your pull request and then a series of actions, CI actions run, okay? So they'll possibly spawn some containers or VMs, which will then unit test your code and run code QL and all these various things. So somebody worked out what you could do was, so the first time you send a pull request to a project, it's automatically accepted. It's not merged, but it's accepted. And CI starts to run to establish the quality of your code, okay? So somebody thought, well, what if I just send some scripts that run a Bitcoin miner? Then the CI will run it. It doesn't even worry about who I am. It will just run it. And for that short amount of time that it works, I'll accumulate some Bitcoin. So if I do this like many, many times and start to generate some bots to do this, there's some money in it. Now, in their favor, GitHub responded really quickly to this, and they changed it so that when somebody makes a first pull request to a project, the CI is paused until a maintainer of the project allows it to go through so they can look at the code. So, you know, kudos to GitHub. They closed that one down pretty quickly. So yeah, as I say, these systems are wide open to for recce, essentially, to look at, and they're open to scrutiny. You know, that's one of the key elements here. So attackers can look at things like integration tests, you know, that create machines and then, you know, virtual networks, and there's all sorts of stuff that happens in integration tests. They can see possible exploits there. And as I said earlier, there's so many instances of people doing this. Here's my project. They want people to use it quickly, so they say curl a shell script down. You've got no idea what that shell script is, and run it as root on your machine. And it's really bad. You know, you're a smart audience, you're security guys and girls, so you know not to do this. But if you just happen to be passing and you've walked in off the street, don't do this. It's really bad. It's really bad. Okay, another one is typo squatting, and I forgot to say we're going to make this interactive. Okay, so typo squatting is essentially you find a name that's very similar to an existing project. Okay, and then you just change a small part of it, so to the human eye, they can't really spot the difference. Okay, but then you're then able to have somebody pull down your package, which is malicious, and run, okay? And this is especially key when, let's take Python, okay? They have their dependency requirements.txt. Some of them have like 25, you know. Nobody reads over all of those, you know. You just don't, you see what I mean? There might be some that do, but they're a minority. So I wanted to just check with you. Anybody, left or right, which is the malicious one? 2 seconds, 1, 2. Okay, you got it. So you probably spotted it's actually the I is swapped out for an L. Now here's one where there's no deliberate spelling mistake. Okay, so probably the Python developers are going to get a bit more of an advantage here. So which one is the actual correct authentic package? Anyone? You're correct, yeah. So the one on the left that's what Linux distributions tend to do. So if you use Debian or Fedora, they'll prepend, yeah, Python 3 to the start of the package. Just helps them for passing out stuff and, you know, stuff like that. So yeah, date utils is the actual correct one. And there was actually a case of a Python 3 date utils that was compromised as well. Okay, so looking at all of this, there's a, should I stop at the line now? Looking into this, there's some common sort of solutions that we could start to explore here, okay? And one of them is transparency, so the ability to detect a key compromise, because as we've seen, they're very difficult to monitor for, okay? Unless somebody really spots it because it's their key, perhaps, and they know that they didn't sign something. But it's very difficult when they are actually compromised to establish that. There's this whole thing of tofu that we described, okay, and trust on first use, and having non-repudiation, okay, around the identity that's making a claim. There is being tamper resistant. Okay, so people can't change digests and manipulate metadata and so forth to cover up any sort of bad actions. And then there's timestamping, okay, trusted timestamping. This can really help protecting against the targeted attacks that I described earlier, such as replay attacks. So I started to look at these and I thought, what would be a useful technology to address some of these concerns that we've seen? Okay, so I had a hunt around, is there anything existing that we could utilize? So this was where I came across a technology called a transparency log, okay? And a transparency log uses an algorithm called a Merkle tree, okay? It's nothing to do with the German chancellor, okay? It's actually Ralph Merkle invented the Merkle tree. And a Merkle tree, they're used quite widely. BitTorrent uses a Merkle tree, Bitcoin transactions utilize a Merkle tree, and Git has a kind of Merkle tree as well, okay? And a Merkle tree, to put it simply, is what you do is you build a tree of hashes, okay? So you have digests, okay? And what they tend to do is, if you have 4 blocks, okay, say you've got a file, you split it into 4 pieces. Let's use the BitTorrent technology as an example. So you've got Star Wars AVI, okay? You split it into 4 pieces, and you capture a digest for each file part. Okay, so now you've got 4 digests. 2 of them are concatenated together, and then a hash is generated of that. And then you step up the tree from 4 to 2. Then those 2 are concatenated together, a hash is made, and then you have your root hash, okay? And your root hash represents the entire integrity of the tree. If anybody tried to tamper with any single part of that Star Wars AVI file that had been seeded, I guess they call it, for BitTorrent, then it would break the entire structural integrity of the tree, okay? And Git does a very similar thing here, and TPMs that we spoke about before, they use this, they call it a hash extend, okay? And the good thing about this is it's computationally very inexpensive to hash stuff. Okay, symmetric hashing is very resource unintensive. Okay, but it's incredibly expensive to try to go the other way. Okay, it's practically impossible. We're kind of getting into the realm of quantum computing and all that sort of stuff. Okay, so this is actually the technology where I noticed this was utilized in an interesting way is called certificate transparency, okay? And certificate transparency has been around for a while. If you don't know about it, chances are you're already using it. So we'll, how are we doing for time? Okay, I'll keep going, okay. So I'm gonna give you a kind of quick context of what certificate transparency is, because it helps frame how we leverage this for software sign-in transparency. So before certificate transparency came along, what you would have is you'd have your website admin. Obviously, this is a black hat in this instance. You'd have your browser, and then you'd have your CA, your certificate authority, okay? So the website owner or admin would say, right, I've got this domain, bigbank.com. Can you sign this for me? Here's my CSR, my certificate signing request. This will go off to the CA. So it'd usually be a commercial corporation like GoDaddy or VeriSign or somebody like that, okay? And they would go, right, let me do some checks to make sure you are who you claim to be. So make a TXT record against that domain. Prove to me that you own that domain, okay? They go, right, we're good. Everything's good. Here's your signed certificate or your bundle, okay? And then you have to try to work out, how the hell do I get this to work in Apache or Nginx, okay? Then what happens is the browser, I'll come back one, the browser then wants to visit bigbank.com. So they ask the CA via the root store in the browser, okay, can I trust? And the CA says, yeah, you're good. Okay, and then everything looks great. You get the green padlock. Okay. Now, the problem with this model is all of our trust is going into this single entity, the certificate authority. Okay. Now, if they're good, it's okay, but we're having to make a kind of a very loose decision of trust there around the CA. Okay. So what a few folks came up with was this idea of a certificate transparency log. And what happens now is, so the certificate transparency log utilizes this Merkle tree. Okay, so certificates are sort of hashed into the tree. Okay, and so we get exactly the same flow as before. I'm bigbank.com. Can you sign my stuff? Here's your signed certificate. And then the browser wants to visit the site. But what happens now is the CA has to put the certificate chain into the certificate transparency log. Okay. And something I didn't mention earlier with Merkle trees, they're immutable. So you cannot change them. They're impossible to change. Okay. So they're considered append only and immutable. Okay. So that goes into the transparency log. Now the browser, when they want to visit a site, they have a header saying expect CT, which is that I'm not going to trust this unless it's in the certificate transparency log. Not so much trust, I'm not going to serve this unless it's in the certificate transparency log. So we then have an extra entity at the top, which is a monitor. So then the monitors can monitor the log for domains being signed, and they can see they have non-repudiation because the certificate that was signed for the website is fixed to a root CA. Okay, so the CA cannot deny that. Non-repudiation means that I can't claim something isn't true because it's provable with cryptography, essentially. Okay. And the reason this came up is because a while ago, Google and Facebook and a few others, somebody went up to a CA and said, hey, I'm Google. Can you sign my certificate? And they went, sure. And then somebody had a TLS certificate saying they were Google on Facebook. So you can imagine the damage you could do the power that you would have if that was given to you. So now the likes of all these big providers, they all now monitor these transparency logs. So Let's Encrypt run one, Cloudflare, Google, quite a few others, they run these certificate transparency logs. So to cut a long story short, I thought maybe we could utilize this technology for software signing because we have some commonalities. We could utilize X509, there's digests. We need an immutable, append-only, tamper-resistant store. Maybe there could be some traction to this. So I wrote a prototype. It was over the weekend. It was July 2020, lockdown. Hey, might as well try and do this. Let's have a go at it. So I wrote this basic system, called it Project Recore. And then, like any open source project, I wasn't really quite sure what to do next. So I started to share it with some people. So there's a guy from the Google open source security team who I'm quite good friends with. And I shared it to him. I said, Dan Lawrence, what do you think? And he said, this is pretty cool. I'd like to work on this. So then we started to collaborate and it started to build. And we built this system called Recore. Okay, so we had this software sign-in transparency log. And we thought, great. And we started to talk to people. And then what we realized was nobody's signing anything. So we can't get people to put stuff in because they're not signing anything in the first place. So it's like, right, okay, well, we thought we had a solution. Now we've got another problem. Okay, so we started to look into who was signing things and in what way. We did some due diligence. And there was the Linux kernel. Predominantly, most of them were using PGP. As you saw, for the Linux kernel, it's tofu, trust on first use. Okay, so if Linux is ever compromised, God help us all. And Node.js, again, all of the public keys are on a GitHub README. They can be changed. Python, they use PGP. Keys are on a website. OpenSSL, same story again. Kubernetes, when I started this project, they weren't signing anything. They're using sigstore now, so we managed to get one of these guys, and we're talking to the others. And we looked at package managers, kind of the same story again. Some had some level of sign-in system, but the usage rate was in the sort of low 2-3%, okay? Rust, not doing anything at all. So if you run Rust up, or you run cargo to pull your dependencies in, they're all being pulled in untrusted, okay? So I love Rust, okay, but the big thing with Rust is the guarantees you get around memory safety and ownership. So it's seen as being a secure language. But the package manager just pulls stuff in untrusted, and and then you compile your project from that. So there's a very mixed picture there. And the predominant thing was that everybody was using PGP. This is probably where I'm going to upset somebody now, okay? PGP is broken. It's not, no, okay, I'll retract that. In certain scenarios, it's very useful still, okay? Like my own company, Red Hat, we sign things with a GPG key, but then we've got a hardware security module that's locked in a room that you need to sign to get access to. Trying to replicate that setup as a small open source project is really difficult, and it's expensive, okay? And the general consensus is, I mean, look, we've got some pretty heavyweight crypto folks here who are just saying it's day's over for PGP, okay? And the adoption has never really happened. I mean, it was amazing technology when it first came out. The idea of you could sign emails, you could encrypt emails, okay? But the majority of people just do not use it. I mean, you're all security folks, and be really honest with me here. Who's got PGP set up for their email? So a quick count, I'd say, is about 8 or 9 of you out of 100 maybe. Okay, so it's just not got the adoption. So we thought we can't really go with that. We need to use a different protocol here. So again, what projects or technologies can we utilize here? Because one of the other concerns that people had was managing the private key, okay? How do I do that? What if I lose my key? What if somebody steals my laptop? So we have to try and solve that issue for them. So for here, I'm talking about the 95% who are not really, don't have a YubiKey and are really into kind of crypto management and stuff like that. So something that's predominantly used a lot is OpenID Connect, okay? And the nice thing with OpenID Connect, you get some very user-friendly security tools, two-factor authentication that are built around it. So for a majority of users, they can get their head around using this stuff. Like my wife uses 2FA for her Gmail account and stuff like that. So it's very easy for the majority to adopt. I'm not talking the hardcore security geeks here, okay? So we thought, how could we utilize this? Could somebody sign something with their OpenID? Okay. So we then sort of pivoted from Recore to becoming sigstore, which is what the project is, okay? And now we have this, and I'm not going to try to walk you through that. I've got an animated slide that'll be easier to do. It's a bit too much to take in, but we combined all of these technologies together to create what we now call ephemeral key signing. Okay, so I'll show you what that looks like. So we have our user, they've got their artifact that they want to sign. There is a new system that we have called Fulcio. This is like our PKI certificate signing system. There's Recore at the bottom that you know about. That's a software sign-in transparency log, the Merkle tree. And there's also a certificate transparency log. Okay, so we've got these various parts of the system. And what happens is the user generates a key pair. Okay, this happens locally. It's ephemeral. It's just, they don't even touch disk. They're encoded to memory. Okay, so they'll create a key pair. In this instance, it's elliptic curve, P256. Okay, they'll then contact our system, and the system will then send back an OpenID Connect session, okay? That user will then select a provider, GitHub or Google or whoever there is. There's about 20 of them, okay? And what they will then do is they'll receive a token and they will sign their email address and send it back as a challenge. Now, we're not taking any security guarantees from that email address. It's just an arbitrary bit of data. What we want them to do is prove that they have the key pair. That's all it is. That could say Mickey Mouse. Okay, so we don't have to worry about the user as the source of the email. Okay, the actual email identity we get from the provider. Okay, so our service will talk to GitHub and they'll request a scope of your email address. So that will then come back, okay? And then what we do is we generate an X509 certificate based on the public key or the key pair that you have that has your email address in, and it's time stamped, and then it's stored and frozen into the transparency log. So we've sort of captured in time that somebody owned a key pair that has an account with an identity provider at a particular time in a very small window, and we put that into the transparency log. What happens is the user then, split second later, they sign their artifact, okay? And the signature, the certificate, and the digest are stored into a second transparency log, the signature transparency log, okay? Now they can discard those keys. They don't have to worry about the private key being compromised because it's very short-lived, okay? And then what this gives us then is a trust root. So you can now verify an artifact has been signed by a particular individual that is in control of a particular account by querying the transparency logs. So you're able to establish that L. Hinds at redhat.com signed an artifact at a certain time with a certificate chain which goes to our root CA, okay? Now, immediately when people see this, they think, well, what if somebody's account gets hacked? Okay, that can happen, but then it's in the public transparency log. So you can then monitor for your email being used. So if your email came up and you'd signed something that wasn't yours, or you weren't aware of signing, and then you'd know, somebody's compromised my account. So we're actually looking at building systems like, have I been pwned? So you can sign up so that if your email address appears, or your identity, then it will blast out to signal alternative email addresses that your identity has signed something. And then that's captured and frozen in time, okay, in a publicly auditable transparency log. So that then gives us a trust root to verify it. And we no longer have to worry about managing the private key. So what we can do then is we can stack consensus around trust, okay? So I can say that I maybe trust something enough to run in my test if one maintainer signed it, but I'm not going to let it run in production until 3 different accounts have signed it. So then you're stacking up the security guarantees by having more entities actually attest that they signed a particular thing, okay? Now, coincidentally, we do cater to the real security geeks as well, okay? So we have like PKCS11 support for HSMs, and we also integrate with key management solutions from the various cloud providers as well. So that previous one, that's for your kind of developers that just don't do security. Do you see what I mean? They're the ones that aren't signing anything. So for them, we balanced usability against security guarantees. And it's a pretty good balance, but if you want to be hardcore and use a YubiKey, you can do that with our transparency log. So in Project SigStore, we've started to create clients. These are the tools that sign things, okay? And one of them is a project called CoSign, which has seen some really good adoption. And this is for signing containers. So you can sign a container and you can discard the key afterwards, and the trust root is captured in the transparency logs. We also are developing a tool called SGET, which is to address the curl bash scenario that I described earlier. So somebody will be able to pull down a file, verify the integrity of that file, the identities that signed it, and then execute it, only if those checks pass, okay? And then we're also working on clients for Ruby Gems. We've got some stuff for commit signing. There's some folks looking at signing WASM modules. The Python community are looking to implement something. We're working with various different communities to build clients as well. So it's really, the project's really blown up. There's a lot of people starting to contribute now. So it's really great to see. The other thing as well, we have our root CA is open. Okay, so when we created our root CA, it happened live on Twitch, okay? And all of the establishing of our root CA is captured in a Git repository, and we had people verify everything. So we had people ask questions like, what's the price of Bitcoin? What's the temperature in Rome today? So that people could obviously see that it wasn't a pre-recorded event, it was happening live. So we use this for our infrastructure, okay? And there's 5 key holders, and it's a mix of academia and corporate. So we've got some folks from NYU and Purdue University, and then there's myself and another guy from Red Hat, and there's Dan from Google. And then if any of us go missing for some reason, we can swap out, because you need 3 keys to swap out a previous key holder. Or if somebody's key is compromised, then we have key compromise resilience, okay? So we can quite relatively easily swap somebody out. So we will rotate people every 6 months, and we're making this available to other open source projects to use for free. So if you need a trust root, you don't have to go and spend how many $100. You can come and see us, and we'll create something for you. So our sort of vision at the moment really is, what we want to do is we want to be to software signing and provenance what Let's Encrypt was to TLS, okay? So an interesting thing happened when Let's Encrypt came on the scene. So previously, there were many, many sites running on HTTP, okay? A lot of personal blogs, even e-commerce sites would run on HTTP. And a lot of this was because it was just hassle to get a certificate. You had to go to somebody, give them money, scan your passport, send it to them, wait for them to reply, prove who you are. There's all this faffing about that would happen for you to get your certificate. And Let's Encrypt came along and they made them free, okay? And they provided the tooling so you could get them like that, okay? And then an interesting shift happened. It became socially unacceptable to run a site on HTTP. So now if you go to a site and it's HTTP, it's like, ew. You're like, am I going to get a virus or something? It just feels a bit dirty. Do you know what I mean? Because everybody expects HTTPS now, not even your power users, you know. So we managed to shift the paradigm. And that's what we want to do for software. That's our vision in SigStore, is so that it's no longer acceptable to pull in packages and dependencies from the internet and run them in your software without them being trusted. We want that to become a bit kind of, that's not good, essentially. Okay, so that's our kind of our driving vision. What we have coming next is we're looking to integrate with more communities. So Arch Linux want to use us for binary transparency. Been speaking to the Arch folks. Doing work with Kubernetes. Bitcoin want to use SigStore to sign Bitcoin releases. They got an issue about that. Ruby Gems, Python, the Rust community, we're starting to approach them. And we're also starting to look at SBOMs. So we're starting to realize this technology is really conducive to supporting SBOMs. So an SBOM is a secure bill of materials. Okay, so it's essentially a log of what's happened to build a piece of software. Okay, and there's lots of people realizing this would be pretty good to build to provide provenance of an SBOM. Okay, and just before I go into that, I just realized one thing that's missing here. So we're running a public service right now, so you can use SigStore to start signing things, but we are not fully launched as yet. We're in soft launch. So what we're doing at the moment is we're seeking funding. Okay, so we're approaching various people to fund us. We're under the Linux Foundation, okay, and SigStore is going to run as a non-profit, free-to-use service for everybody. Okay, there's not going to be any pay more and get a special tier. It's for everybody to use. This has to work for everybody. It's got to be easy to use and it's got to be free. And that was one of the core asks that I had for this project, was that if it's going to work, it needs to be non-profit driven. Okay, so what I'd like to say is a kind of a little call to action is, if you're interested, do approach me. Our transparency log is open, so lots of people are looking to build security systems on top of that, because there's all sorts of interesting data sets that you can get at. You can monitor for your clients to look for key compromise, software, bill of material, provenance, and so forth. If you need stuff signing, come and see us. Okay, we're always really keen to work with people. And we are a really, really like friendly community. We mentor people. You don't have to be like a security engineer. Documentation, sysadmins to kick the tires, get things to work, report bugs. So we really are a welcoming place. So I do encourage you to come along. And if you need to get in touch, we have our website, sigstore.dev. Okay, you'll find everything you need there. And then all of our code is 100% open source. Okay, so you can come in, you can read the code. Quite a few of you are security researchers, and you'll probably be thinking, I might go and have a look in there, you know. So we do welcome that. What we'd say is we are quite early in, and we're not going to go into production until we have a thorough set of scrutiny from some people that are going to come in and do a threat analysis and look at the code. And so, but if you do, we run a responsible disclosure program. So that means you'll be able to get in touch with one of us, okay? And then we'll handle it under embargo to make sure that systems are patched and users aren't put at risk, essentially, okay? And so, yeah, anybody that's interested, do come along. And I'm right on time. Thanks for having me, everybody. It's been great. Really enjoyed meeting you. And thanks again to the folks that put this on. Cheers.